Hey, welcome to this month's Power Hour. Today we're going to be talking about one of my personal favorite topics, evaporative emissions. Now, it wasn't always one of my favorite topics, and maybe it's not one of your favorite topics today either. I remember, as a technician in the 90s, we started hearing about OBD2 and evaporative emissions, and it's going to test the fuel system to tell if there's a leak and how's that going to happen, and then the evolution of smoke machines and where that whole world has gone. But once I dug into it and learned how these systems work, how the monitors run, how to test them, how to repair them, and how to retest them, rerun that monitor before giving the keys back to the consumer, I really learned to enjoy evaporative emissions diagnostics. And so today we're not really going to talk a whole lot about just evaporative emissions, but we're going to narrow it into what about turbocharged vehicles with evaporative emissions? There's some different nuances here. We've got some check valves, we've got some pumps. A lot of different stuff has to happen on a vehicle with a turbocharger, or I guess for that matter, if it had a supercharger. And so that's going to kind of change our direction on some of these diagnoses on EVAP systems. So that being said, let me head over to the bench. Let's get started. All right. As mentioned, today we're talking about EVAP diagnostics on turbocharged engines. So it all starts right here. Very rarely do we have consumers coming in saying, hey, my car's running bad because of the evaporative emission system. Now, again, back in the day, we used to have a fair amount of that. Remember the old Purge solenoid sticking open? The car would run terrible or it might flood out. A lot of stuff might happen to it because of Purge fault or flooding of the system with it. But in today's vehicles, these systems are so tightly monitored. Really, the first point of contact there is going to be with the check engine light. So if we look at this from a regulatory standpoint, why do we have this stuff? Well, it all goes back to the EPA and coming up with regulations. Now, we're at a little bit of a disadvantage here because the EPA and CARB didn't really say to manufacturers, you need to do this, this, and this. That's why today we have some variety on how different manufacturers use different strategies and different components to diagnose the EVAP system. Really what these regulating agencies are saying, you need to check for a couple things. First is you need to make sure that there is purge flow. So when purge is commanded, purge needs to happen. Now we see different manufacturers do this, whether they're monitoring the fuel tank pressure, some will actually have a flow sensor built into them, etc. So that's one thing they have to monitor. The next one is they have to verify there's no leaks in the atmosphere. And certainly as we've seen the evolution of vehicles and regulations, those regulations have gotten tighter and tighter. And so the systems have to be monitored closer and sealed tighter. And then finally, the components need to be monitored for circuit connectivity or continuity. Got to make sure that the ranges are kind of where they should be. If it's a 0 to 5 volt system, it shouldn't probably be at 0, shouldn't be at 5 volts, but somewhere in between there, or we certainly don't want to see 12 volts on that. That kind of goes along with the next point of rationality. Does what we're seeing make sense here? Then check for proper functional response. Hey, I commanded it to do this. Did it do that? How are we seeing that? So let's kind of go back to just base evaporative emissions here. Really two core components if you think about it. We've got the canister, which is going to be vapor storage. That's going to contain the vapors and release them. That's the goal of this. How's it released? Well, it's going to be released through the purge solenoid, which is going to draw those vapors from that canister into the engine and allow them to be combusted or burned up with normal combustion here. And so those are really two of the key categories or two of the key components in the system. So when it comes to vapor storage, we look at the schematic here, we can see the fuel tank, and on the upper right, we've got the fuel neck. So imagine a tank is empty or relatively empty. It's like anybody in my family, the tank is definitely empty. It's down to 3 miles to go before we need to fuel it up. Now a refueling event occurs. So fuel goes into the tank through that filler neck. Now what happens? Well, there's air in there. That air contains fuel vapors. And so that air has to go somewhere. We don't want to just let that vent out into the atmosphere. So at this point, that air is going to be forced through the EVAP system to the vapor canister. That vapor canister will have activated charcoal in it, and it's going to adsorb the fuel vapors. It's not going to ab with a B, it's going to add with a D, which means it's going to stick to the surface. It's not going to completely act like a sponge and suck it in. This activated charcoal is going to adsorb. So the hydrocarbons will stick to it, kind of filter it out, and we're going to send clean air out through the vent valve at this point. So it's kind of filtered the hydrocarbons out of the air. Now, once that canister gets full of these hydrocarbons and vapors, we don't want liquid in there, right? That's going to create a problem. You might be thinking of some of those customers, and we all know the person that wants to get it up to the even dollars, so they keep clicking, putting more fuel in. Fortunately, today's tanks have the rollover valve, which quite often will prevent that, but not always. So if we've got this full canister, we need to get rid of the hydrocarbons inside of it. And so that's where the purge solenoid comes into play here. It's connected to live intake manifold vacuum. And so when the time is right, the control module, usually the PCM, is going to command that purge solenoid to come on, and it's going to draw a vacuum or apply negative pressure to that line there. And so what's going to happen is fresh air will be drawn in through the vent into the canister, and the air is going to mix with the hydrocarbons or the fuel vapors in that canister, and it's going to draw them all the way into the intake manifold, where they will ultimately be burned up. So this is your traditional system layout here. Again, we've got the fuel tank on the right-hand side. Now we've inserted the fuel tank pressure sensor. That's what most manufacturers will use to monitor the pressure in the tank. Not necessarily the fuel pressure, but the vapor pressure. And that's what's going to be used to monitor if the system is sealed on a lot of the older traditional ones. Different ones now, we see different styles such as eSIM, etc. But the traditional ones utilize that fuel tank pressure sensor. So we've got that. We've got the vent valve, which is going to be normally open, right? We want that thing to breathe. Yes, we're going to test to make sure it's a sealed system. However, the original design of this is to allow that to breathe. We need fresh air coming in and out of the system through the vent valve. Then the purge solenoid is going to be normally closed. That's blocking the system from accessing the engine vacuum there. But when the conditions are right, typically it's going to be steady state cruise or maybe light acceleration. The PCM is going to control the purge solenoid on, and that's going to usually send a duty cycled signal to that purge solenoid to command it on to open the passageway and apply the vacuum to it. And that vent valve will be open. The time when the vent valve is going to be closed is when we're doing the system test, the leak test. Everything should be closed at that point, or maybe a purge will be applied to it to draw a little bit of a vacuum. But that's a little bit of the initial review on how EVAP systems traditionally work. Yeah, there's a lot of different varieties to them here, but that's kind of the traditional system. So if we were in a live class here sitting in front of an audience, I could see all face to face, this is where we'd open it up for discussion. What about on a turbocharged engine? Typically at idle, the manifold is going to be under negative pressure, also known as vacuum. However, when we're accelerating and now boost is applied to the intake manifold, what happens? What changes? You're absolutely right. We've now got a positive pressure, and so that pressure is being increased. So what's going to happen if all of a sudden the purge solenoid is turned on when the manifold is under pressure? Well, it's going to start blowing that pressure backwards, and we don't want that to happen. Neither do the design manufacturers who came up with this stuff. And so they got to do something different here. We have to figure out a way to purge, to get those fuel vapors to go into the manifold, even when it's under pressure. So what did manufacturers do? Well, there's a couple different strategies here, and different ones use different ways. But the first is to have a purge pump. And so that's going to apply positive pressure on the purge side, kind of build up a reserve there. So when the purge opens up, the pressure will be greater than the boost pressure in the manifold, so it will flow in the right direction. Other manufacturers use a single check valve. And what that's going to do is prevent the pressure from going back. So that's a very straightforward, somewhat rudimentary design there. Other manufacturers, we're going to get into this in a little bit, use what's referred to as a dual path flow. So there's a couple different ways in which you can go here. Those ones might be a little more tricky to diagnose. I'm going to explain how those work. The good news is, at the end of the day, it all comes as one assembly. So you really have one part to diagnose and replace here. So let's start out with the pump style system. Now, I happen to have one hiding behind my keyboard here. And so this is utilized by GM. So this is a 2017 Chevy Silverado. So again, you look, we've got kind of our same drawings, what we had there with the fuel tank, the vent valve, the vapor canister. But if you look in the upper left now, we've added an EVAP Purge pump. And then we've got the Purge solenoid or the Purge valve, which you mean normally closed, right? And then it's going to be connected to the turbo inlet. So we've got a new component, but how does this work? Well, as the vehicle is driving, we've got the canister, quote unquote, relatively full, and it's filling full of vapor fumes. It's time to purge. Now the vehicle is going to ready itself and prepare for purge operation. So it's going to energize this purge pump here. Relatively straightforward, electric motor in here, and it's going to build pressure. You can see about 7 to 10 PSI. I'm going to show you some scan data here in just a second. So it's going to build pressure in there, and now the purge solenoid is still closed. So in the line between the two components, it's building pressure. So now, once that purge is commanded, we've got a reserve of pressure here, and it's going to force that into the intake manifold or the turbo inlet at this point. And so it's going to have a positive force pushing it into there. So this is a known good data capture from the same Silverado here. You might recall last year we did a power hour and kind of studied a little bit more about the intricacies of this 2.7 liter GM engine. So on the top there, you can see engine speed. Now the cursor is placed about in the center of the screen here. Right below it, we can see map pressure. Then you can see the purge solenoid on or off. And I mean on or off. Traditionally, with purge solenoids, we would see them kind of ramped up, 10, 20, 40, 60, 80%. Look at this one. It's almost like a duty cycle. I mean, it's going from 0 to 100% at this point. Now you can see the EVAP Purge pump. And so that black line there, third from the bottom, you can see most of the time this thing is turned on. It's building pressure in there. And so when it's time to purge, it's got the pressure. And we can see that in the second to bottom PID there, EVAP Purge or EVAP Purge pump pressure sensor. And so it's building pressure in there. And if we look at the final PID on the bottom, that's our fuel tank pressure sensor, all the way in the back of the vehicle. And so that indicates that this thing is doing its job. That tank pressure should drop as we're purging, correct? And so if this was bad, it would go the opposite direction or nothing would happen there. So this is just one example. And I invite you to refer back to this next time you're trying to diagnose one of these things. But at the end of the day, it's commanding that pump on, it's building pressure, as we can see in that second to bottom PID there. And ultimately, it's pulling a vacuum on the tank. It's getting those fuel vapors going from the tank through the canister all the way into the intake manifold where they'll ultimately be burned. So an even better tip, if you've never worked on one of these things, take a look at this next time you're working on a 2.7 liter GM engine. And you're going to see some awesome data PIDs here that are going to really help with your diagnosis. You can see we've got a kind of a cutaway here. Engine speed, EVAP pump purge, desired purge pump speed. A little bit of a tongue twister here for me this afternoon. And then purge pump speed actual. So we've got desired and actual, which as a technician, I always love seeing desired and actual PIDs. In this particular one, it's asking for it to go 43,000 RPM. Yes, 43,000. And the actual is 0. So as a technician, I'm going to test my powers and grounds, maybe even tap on this thing a little bit and see if it wakes up and starts working. Good news is these early applications, it's a pretty big failure. And so if you've not diagnosed one of these, next time one comes in, I don't want you to just call the parts store and order one and install it yet. Go through the diagnosis here, look for the data PIDs for it. But very commonly, it's going to be the fault of this particular pump. All right, well, now let's move from that pump to the check valve systems here. Personal opinion, humble but probably accurate opinion, as a matter of fact. GM has been really straightforward for many years. Now, growing up myself in Michigan, working as a technician there, we had a ton of GM vehicles at factory tooling, really my whole career for GM. We had a lot of data given to us. GM just kind of seems to do things relatively straightforward. Same can be said here for this. We have the purge solenoid. Between the purge and the intake manifold, there's a check valve. Again, pretty straightforward. Just making sure that if the system is under boost and the purge solenoid's turned on, that boost can't go back to the purge solenoid and back to the tank ultimately. And so a check valve will prevent pressure from going backwards, but it will allow the vacuum to go through. So, not a real difficult head scratcher of a system. You've probably replaced plenty of these. You see them. You can see the check valve is molded into the purge valve here. And so as it's located on the intake manifold right there, relatively straightforward replacement. I've actually got the one here on the bench. This one didn't have a check valve on it, but quite often you'll see this and it'll have the check valve incorporated into it a little bit further upstream. So here's a known good data capture on a Chevy Cruze, the 1.4 liter turbo. I've got the turbo sitting right here on the bench. Actually, next month we're going to be talking about turbo or forced air induction vehicle. So this really goes hand in hand with it. But on this 1.4 turbo on the Chevy Cruze, you can see the engine RPMs on the top. You can see the purge command right below it. Now, we don't have a pump, et cetera, like we had before. So this is pretty straightforward. If you look at the map sensor and the boost pressure down below, when is this thing purging? Look at that second line compared to the bottom line. You kind of see where our cursor is right there. This thing is purging when it's not under boost. When boost starts to build, the purge solenoid shuts off. So it's a pretty straightforward strategy in these particular vehicles here. If it's boosting, it's not going to purge. If it's on deceleration or light acceleration, minimal boost, it probably will purge at that point. And so the check valve is used here just to make sure that pressure is not going back to the tank. Now let's look at Ford with some of their systems. And a little trickier, but if you wrap your head around it, it's pretty straightforward at the end of the day. So the first method here, Ford will refer to as a single path system. So I'll give you a couple seconds to kind of take this all in here and look at the schematic. On the top, we've got the intake manifold. You can see the throttle blade to the left of it there. And then we've got the purge line with a check valve. So very similar to GM. It's going to be connected to the intake manifold there. All the way to the left, we've got the charge air cooler, the turbo, drawing fresh air in, obviously, from the air filter. On the right-hand side, we've got our fuel tank, our canister. It's going to be connected to the CPV is canister purge valve or canister purge solenoid here. And then it's going to draw it up through that check valve to the intake manifold. So this is almost identical to the GM system. It's just drawn a little bit different in this particular image. So if you understand the GM one, you understand the Ford single path system. Now, let's make it a little more difficult here. Now, the dual path system. So on the right-hand side, everything's the same as what we just discussed, right? You've got the canister purge solenoid. Then you've got the check valve there. But to the left of that, kind of in the middle, you can see check valve 2 and then the ejector line there. The way that ejector line works is kind of off the Venturi effect. And so if you look at the turbo on the left-hand side there, that's going to create boost, going to create pressure. And so that boost is going to go through the charge air cooler. Now it'll come through the line there. So pressurized air is going to go through that line, follow kind of where that purple arrow is, going to go through the ejector. And that's going to have that Venturi effect, and it'll draw those canister vapors from the purge solenoid through that check valve and then through the ejector. And then that's going to deposit them, yes, in front of the turbo at that point. And it's going to be drawn into the engine and combusted at that point. And so this is relying on the Venturi effect. So this is what I've got here on the bench. We can see we've got the purge solenoid. We've got our check valves and our ejector circuit here. So, there's a lot to this. Here's the other check valve. And so, again, this looks like a lot here. This is going to be coming in a box tube. And so there's a couple clips here, a couple places to clip it on. But really, we've got 4 connections here, 1 electrical connector. And so it's kind of an all-in-one, if you will. So if you got one bad check valve, you don't have to determine which one it is. So let's kind of work through a diagnosis here quickly. Then I happen to have Corey brought his kid's car in here. And so we're going to kind of just demonstrate it under the hood here. So we've got a broken vehicle. It's 2013 Ford Fusion, 1.6 liter EcoBoost, 64,000 miles. As with most EVAP concerns, the customer's only concern here is that the check engine light is on. Something must be wrong with the car. It runs fine, but that light won't go out. Technician does his due diligence, starts by scanning the vehicle, and right away we've got a different code. We've got a P144C. Now, many technicians are familiar with a P, but then usually it's this number. So we've got P144C here, and the code definition is EVAP system purge flow performance during boost. So that's kind of a unique qualifier there. And really, that's the world we live in today, right? We've got so much data, so much sensors at our fingertips here that the vehicle can really specify in set a trouble code based on the information that's received there. So technician looks up the code description and service information. And so we can see that the check valve test is performed during minimal boost conditions. So it's not wide open throttle, 30 pounds of boost, nothing like that. Only once per drive cycle when the entry conditions are met. It's got to be the right amount of fuel level, right amount of ambient temperature, etc. This DTC sets when the tank pressure exceeds a calibrated amount within a specified time during that test. So in my mind here, already started to put the game plan together of it's building pressure in the tank during boosts. Okay, my mind goes immediately to this assembly that I just showed you here. And so if we look at the causes here, stuck open, check valve, stuck closed, check valve, damage EVAP ejector, damage EVAP check valve. So kind of redundant here, but the good news is almost everything that's listed there comes here. And so it's a 4-in-1, if you will. So again, from a technician perspective, by understanding the code setting criteria, we're kind of thinking here, the system's going to compare atmospheric pressure with tank pressure. And then it's got too great of a differential here. So this technician is going to take the vehicle for a test drive. And I'm going to note he went ahead and cleared the trouble codes first. Now, I know through the years, we've always taught, do not clear trouble codes until you've made the repair. I'm going to say, go ahead, once you've recorded it, clear the trouble codes. You stored the information. You've done the stuff. Quite often, different monitors are going to be inhibited because the trouble code is set. So by clearing those monitors, you've now kind of opened it, and in many cases, forced the monitor to run here. So the technician drove the vehicle. Check engine light did not come back on the test drive, but he's recording the data on his drive. So let's take a look together at what he sees. Now we've got engine RPM on the top. We've got the purge duty cycle, the second line. And so again, it's a pretty drastic purge. It's really throwing 100% purge at it most of the times here. Then we see the fuel tank pressure. This is not, fuel rail pressure. This is the atmospheric or the inches of water shown on the fuel tank pressure sensor. And right there, it really tells a story in that green pit. We should always be drawing a vacuum. Or if we're doing NVLD testing overnight, natural vacuum leak detection, we might see 1 or 2 inches when the vehicle's at rest. But look at here. We're building boost, we're purging, and now we're building pressure in the tank. That's really a slam dunk that we've got a fault with one of these check valves here. So again, by looking at the system, you can see we've got the multiple check valves there going to the ejector. And so technician really comes to the conclusion, it's a problem with the check valves. So as we look underneath the hood, you can kind of see on the left-hand side, there's that orange tag there. That's kind of part of it. And then in the middle, we've got the purge solenoid. Once again, this all comes as a one-piece component. So the technician gets customer approval. He's going to go ahead and replace it. And then this is the important part. You got to do a verification afterwards. Let's test drive and make sure it's not doing what the customer said it was doing, or in this case, what the PCM said it was doing. So if we, once again, clear out the memory, we're going to drive the vehicle. I think we can all agree that now when we see the purge commanded, the fuel tank pressure is going negative. And so it's drawing a true vacuum on it at that point. So to me, this sounds like a successful job. Technician did the job properly. So we happen to have a vehicle similar to that here. You know, it looks great when we do it on film like this, but I'm going to ask Corey to go ahead and start the car up in a second. Perfect. So we've got the car running. I'm going to have him come over here over my shoulder.
Okay. So I've already kind of pulled up the menus here, selected a couple data pits. So we're going to watch the duty cycle, the tank pressure. You can see the engine's running. But actually, if you look over here, you can see some of the components. They're very, very straightforward, easy to get at here. If I pop this cover off, again, this is right in front of us. So we've got the vehicle idling here. It's already purging at 10%. If I ramp this up here a little bit more, I'm in just active tests. I didn't have to go into special functions, anything like that. But I'm ramping this up here. And so now we can see we're starting to pull a little bit of a vacuum on the tank. Now keep in mind that the vent's probably actually open. So we've got some resistance in there. So we're actually pulling a little bit here. Now, again, we're not boosting at this point. But if I was really going to be checking for that, I would probably rev it up a little bit, apply some boost pressure, maybe even power brake it, and monitor my fuel tank pressure. It's really that simple. So we're going to monitor the fuel tank pressure while commanding purge. If it's building pressure, well, we know we've got a faulty check valve. It's truly that straightforward. All right, well, let's go ahead and shut the car off before we
get too much carbon monoxide in here. So, kind of wrapping things up here, a couple of key takeaways. We can't forget evaporative emissions fundamentals, just the basics of the system. Remember the opening reasons why we are testing these EVAP systems. But now we have to consider having positive pressure. We've always had negative pressure, which is vacuum. But now with boosted systems, the system will, under the right conditions, be under positive pressures here. By understanding the system, knowing is a single check valve, is the dual path, does it have a pump? Understanding how the system works is going to give you a huge heads up on your diagnosis here. And just like with any repair, you know, if you replace a radiator, I'm guessing you're going to check for leaks afterwards, right? Or the AC system, you're going to make sure it works. Quite often with EVAP systems, a lot of times technicians forget to retest. They just clear the codes and hand it back to the customer and kind of duck out and hope it doesn't come back again. So that being said, hopefully you learned a lot more about evaporative emissions on turbocharged vehicles. I see a couple questions coming here. Again, Corey's been doing a good job answering, but any of your personal favorites that come out here?
You know, there was one that came up, and I actually have a question on this myself. The EVAP pump you talked about, is that like the old LDP pumps, or is that really just its own electric motor or standalone?
Right. So this is a electric motor inside of there. I'm going to guess it's probably even a brushed motor. The old LDP, like we saw in Chrysler, that was more of a pump style, and so that would build pressure in there. This is more just an electrical motor, almost like a fuel pump or a fan, etc. in there. So Remember that one data pad where it was up to commanded for 43,000 RPM. So this thing's going to spin pretty quickly there. Another question, well, this is probably a somewhat of a theory related to general EVAP, but how come we see more EVAP failures in the summer than the wintertime? That's a great perception. One, it took me probably a couple of years to kind of understand myself. But if we think about the enabling criteria, when is the system monitored? Now, again, I spent most of my career as a technician in Michigan. And so if it's cold for 6 months out of the year, it might be too cold to run the EVAP monitor at that point. And so if we think back to the general purpose of evaporative emissions, well, it's to contain that fuel vapor. When do we have more vapor? Obviously when it's hot. And so during the summertime, we're going to have more volatility, more fuel vapors being generated, and then obviously more fault codes being set at that point too. So the warmer the weather, the more EVAP failures we're going to be seeing here. So if you're looking for more information on this, we've got a ton of resources available on our YouTube channel. You can see here, I just even searched EVAP. So we've got a lot of how to install the parts, a little bit more about our components, our systems, the products we manufacture, as well as previous power hours that kind of touch on EVAP in general. And then as always, I recommend you go to standardbrand.com. We've got a feature on EVAP for the next month here. You're going to find some interesting information there. And feel free to always check out our products. So at the end of the day, I appreciate you spending some time here with us today. And remember, when OE fails, trust standard.